Hello, everyone. We are about to start the second session. And for this, I would like to invite Dr. Debashri Ghosh. Ma'am, please.
Thank you so much. And I would like to thank the organizers for giving me this opportunity. So this session has 3 talks. The first talk is by Professor Ayan Datta from IACS.
First of all, let me start by thanking the organizers, my very good friend Ashwini and Nilanjana, and also currently the chairperson of this session, Dr. Debashri Ghosh. So today I'm going to talk about this, very subtle effect which we call the Pseudo Jahn-Teller effect in two-dimensional systems. So I will come to the system, but before that, let us have a little primer on this thing which we call as graphene. I mean, graphene is something which has changed the landscape of condensed matter to a very, very large extent. Now, when we talk about graphene, we talk about systems which are fused. We can think of carbons, hexagonal carbons, benzenes, and which are fused together laterally. Not necessarily graphenes or polyaromatic hydrocarbons are not really made by stitching benzene rings the way we think of them as computational people. But yes, people are even trying to think of making very, very big polyaromatic hydrocarbons. People talk them as carbon nano flakes of particularly the group of Klaus Mullen, who tries to actually stitch benzene rings together to make polyaromatic hydrocarbons. So typically graphenes is made by physical techniques, the way you typically made. You make them by what we say, you get a black soot under, whenever you have black soot under carbon. In fact, when you go out in a polluted day and when you wash your face, what comes out of it is that the dirt, most of it is actually graphene like materials, right? So the reason why graphene has been in so much of news, because they are Dirac materials, and I will come back to tell you why they are called Dirac materials, because the electrons and the holes they move very fast. I mean, do they really move as fast as the speed of light? Nowhere. The speed of particles there are about 3 orders of magnitude weaker than the speed of light, but we still call them Dirac materials because they are the fastest where the electrons can travel. Now, the question which we wanted to ask, and we have been asking this question for some time now, that why only carbon? What is so special about carbon which makes graphene? Or why can't we even have, let us have consider a Jahn-Teller case where we will have silicon, or we will have something like silicenes. I mean, hexagonal rings made up of silicons. What is wrong with that? And there is a good reason to talk about silicon, because even with all the great effects of carbon, most of your mobile phones and all the processors which you have are still made up of silicon oxides. And the best organic electronic material with FETs would be about 4 to 5 orders of magnitude. The transport properties are weaker than that of silicon. So the question is, what is wrong with silicon? Is, of course, we know that silicon, when we talk about delocalization, we talk about 3p orbitals, and the 3p orbitals are far away from each other, and the pi orbitals, the sidewise orbit overlap of the pi orbitals are weaker. So when we talk about two-dimensional silicon, of course, there is a very strong issue of sigma and pi mixing, and how do we mix the sigma and pi mixing, and particularly, so the sigma manifold and the pi manifold of the energies are actually mixing with each other, not in terms of symmetry, but in terms of energies. Okay. And of course, we were not the first person to do it. In fact, one of the first references which I found, where people were actually thinking of, can we have two-dimensional silicon? And this is also a message to the young people in the audience. See, this is also something how the literature changes. Look at it. This is 1994, and people are talking about silicon and germanium analogs of graphite. People are talking about graphite. These are all monolayers, but people have no idea that one fine day you can actually peel off one layer, and then you call them as graphene. So those days people were calling it as graphite, not even thinking that you call them as graphene. Graphene became very fashionable only when people could actually peel off like your scotch tapes, right? You put a scotch tape on your pencil lead and just take them out, and you get, I mean, don't get one layer, but you get a few layers. And then you do a simple Raman spectra, and then by looking at the Raman spectra, when you see the G and the D and the G bands, and then you see that probably it is a monolayer. So there were evidence. There is also work from India, Professor Umesh Wagmare, who have been who had looked at some of the silicines as two-dimensional system. But the real subject picked up when the group of these are surface physicists, Guy Lilly, who actually found out Dirac cones. In fact, the paper says silicon compelling experimental evidence for graphene-like cones, Dirac cones in silicon. So what these experimentalists have found out that when you have monolayer silicon, sp2-like, you have Dirac cones, and that is something which people would say then you can really have two-dimensional system which are analogs of silicon. Now, being chemists, we wanted to look at this problem from, I mean, we would say a bottom-up approach. Now, do we really have examples? Consider the case, we have benzene and we just knock off carbon atoms and start putting silicon. Can we really do that? Well, yes, organic chemists, particularly from Japan, have been looking at this problem for a very, very long time. Look at this molecule. This is benzene, and one of the carbon atoms have been substituted by silicon, synthesized. This is naphthalene. One of the carbon atoms have been substituted by silicon. Now, there are two issues here. Being experimentalists, you know that a carbon silicon bond is very, very prone to oxidation of under any moisture it will pick up. So what they have done, they have added a very big bulky group so as to make the molecule kinetically benign towards aerial oxidation. These are experimental limitations. Now the question, and this is a place where I think as a theoretician we can make a contribution. Now you are going to ask me the question whether this molecule with a carbon, with a silicon instead of a carbon, and it is stable, is it a consequence of this big bulk, or is it an inherent property? Now this is a very good thing. We can always do a small computation and to see whether even without those bulky groups, these molecules are stable or not. This is a very simple question which we started to ask. Now this is way back in 2010. When I had a summer student coming from NICER who visited me. So we thought we'll look at this problem. And what we found out that we have benzene, and then we go all out to hexacillabenzene, and then we found out that you could actually knock off few of the carbon atoms, and beyond after that, the molecule no longer remains planar and the molecule becomes buckled. In fact, this was published in the first issue of Journal of Physical Chemistry Letters, which was published. You can see. So the question was, is you can substitute benzene, one of the carbon atoms of benzene, by silicon and still maintain planarity. Now, of course, the second question which would obviously one would ask, how many such carbon atoms can be substituted by silicon and still maintain its planarity? Now, when we talk about planarity of benzene, we know we are talking about a quantity which is called aromaticity, right? We know that aromatic molecules are stable, not necessarily that they smell, but aromatic molecules are stable because they have a highly delocalized pi electron system. So this is a question which you wanted to ask: how many carbon atoms can be replaced by silicon and still retain its planarity? And the answer which we had here is you could replace two of them and still remain planar. Now, and interestingly, after our publication, there was an article by Seskevich's group in which they have found hexacillabenzene, and which hexacillabenzene was puckered. Of course, I mean, what was the problem? The problem is, of course, you have a very big bulky groups here. You need bulky groups, otherwise this molecule will be oxidized. But the question is, calculations without the bulk also said that the molecule is puckered. So what we said is puckering is an inherent nature of the system. That is the point which we, at that point of time, we concluded. Now, this is what we also find. You have benzene, and if you look at the phonons, and if you look at the phonons with respect to the wave vectors, you see you have vibrational instability when it is a planar silicene. Well, when it gets buckled, right, the vibrational instabilities are removed. No, this is an infinite. I mean, this is a periodic system in K space, right? The other thing which we found out was when you have silicene, when you have all the 6-membered rings, And so what I have told you, hexasyllable, I mean silicene, where you have an infinite sheet of benzenes is buckled. What we found, when you dope it when you put lithium atoms on the top and bottom, the molecules, I mean the system suddenly becomes completely planar. Now we have to explain this. Now we have two things to explain. One, why is silicene buckled, and why suddenly when you put lithium atoms on the top and the bottom, it becomes flat. So we need an explanation for both the phenomena, both the computational phenomena. Interestingly, and this is something which we had not known that time, there is the phase of silicene. In fact, this is a calcium silicide in which there are calcium atoms on the top and the bottom, and you see that the silicene rings are perfectly planar. So this is also a small motivation for computational chemists to talk more with experimentalists so that we can get good ideas. Vidyaji is in the audience, so I only thought that if I had talked to experimentalists that time, we could have actually known that calcium silicide is the phase. You don't need to do lithium. I mean, the reason why we did lithium was very simple, because lithium had less number of electrons to do with. So we were just trying to be misers. But in other words, what we ended up was being, as I said, yeah, penny wise, pound fool, right? So computational, and this is something which I learned by my thing, that I think we should make approximation and work on the systems which are realistic. Otherwise, we go very close to the solution, but not yet reached it. So the question is, yes, there is this phase of calcium. So the phenomena is real. We have silicene which is planar, and we have silicene which is buckled. Planar when it is doped with ions, and we have silicene which is buckled. Now we need to explain both the phenomena, right? Now this is where there is a very old theory, and the theory is, I mean, the theory, you can work with a two-state model, and the theory is simple. If the ground state and the excited state, and if they are vibronically coupled, what will happen is that interaction between the ground state, and this is just a simple two-state model, you can have even a more complicated model. So the ground state or the excited state would interact, and as a result of the interaction, the ground state would become instable, develop an instability, and the force constant, this is the primary force constant in the absence of any vibronic constant. So as a result, because of the force constant, and this is the gap, so smaller is the gap, stronger is the coupling between these two states, and as a result, the ground state will become vibrationally unstable, whereas the excited state will become more rigid. And there are numerous spectroscopic evidences which have shown that this is true. Molecules which are not really degenerate, that's what we call it pseudo Jahn-Teller. Molecules or electronic states which are not really degenerate, but states which are sufficiently close in energy do perturb each other. As a result, the ground state can be destabilized, can develop an instability, whereas the excited state will become more rigid. And how do you experimentally prove it? You look at the vibrational spectra of molecules, and you look at those modes, and you will find when you excite a molecule, those vibrational modes will become rigid because the excited states are rigid, whereas the ground state will become destabilized. So now, how do we explain our phenomena? Consider the case of hexacillabenzene, and in fact, we can even extrapolate the same logic for silicene. So you have a state, and the distortion. When we look at the distortion was a B2G mode, buckling mode. So the mode which will take me from this structure to this structure is a B2G mode, and the only mode which can interact with the B2G are these two. The ground state will be an E1G, and the excited state, the excited electronic state, I mean corresponding to the electronic orbital corresponding to that state would be that E2G. So the E1G and the E2G would interact via the B2G, which has a gap of about 6 electron volt. Now when you put ions over it, of course we know because of charge transfer the states are separated further, and we know from this very simple interaction model, further are the two states, those states will not interact because the vibronic coupling, the gap between the state comes in the denominator. So this is exactly what we found. So as a result, the reason why graphene, or for that matter benzene, is planar, because benzene also has a B2G state, but the B2G state is far higher in energy, so there is no effective interaction. Whereas when you go, as we know from the group, carbon to silicon to germanium to so on, as you go down the group, interactions are increasing, things are becoming metallic. So now there will be more and more states which will interact. As a result, as you go down the group, things will become more distorted, right? So this is the simple picture which we have for benzene. Well, benzene also has a B2G state, but look at the number, 8.48 electron volt, too far away for any interaction. But now look at silicene, 3.4 electron volt. Now they can interact. So now the prediction is what happens in the case of germanium? Well, they will interact even further because the states are even closer. So this is something which we have. So other words, now we also actually computed the vibronic coupling constants between them. And of course, we see that both of them, silicene satisfies the condition of buckling. So as a result, silicene was buckled. And when we looked at it, germanium was not discovered. I mean, nobody had reported germanium that you can make two-dimensional germanium. But what we said at that moment of time, one fine day if germanium would be discovered, that would be buckled. That's all what we made at that time, right? So then, of course, we wrote that the chemical properties of silicenes would be very, very different from that of graphene. And so that is the point. And then, even without our knowledge, people started reporting buckled germanium. And we knew that germanium will be buckled because the states are close to each other. And there has been a lot of paper now on germanium. And in fact, they say that graphene has a new rival. So same thing now we thought there is now, once we have a simple theory to work out, now the best thing which a chemist, a computational chemist, has a periodic table. So let us try our models on all of them and let's see whether our toy models work. So of course, this also tells us one more important thing about the chemistry of silicon. We said that silicene is going to be buckled. So if a single layer is going to be buckled, if you now start to bring two layers, you know these two buckled layers will come close and there will be almost no diffusion barrier because they are buckled, the electron density is localized on those, and so they will just stuck and it will form what is called the bulk silicon, right? This was, this is a natural outcome of it. And you see, Professor Satyamurthy has actually shown there is a phase transition between these two phases. So if you go, and so the idea is, the example, I mean, this is a very cute work. See, we all know that molecules like two benzene rings, they have what is called a pi stacking. They don't form bonds, they don't form what are called Tiffin box structures. Professor Satyamurthy calls them as Tiffin box structure. Now, when you replace some of those carbons and put silicon, now of course they get buckled. Now of course they come and they form a layer. So of course our interpretation to it, now this is the model in which the system would form a solid. So this explains why there are layers of graphene in graphite, whereas there is no graphite equivalent in the silicon chemistry. So that is the broad take home message. Okay. The other thing which I was trying to tell you, one can always extrapolate this story, and we know that phosphorus has many phases. Interestingly, there are two phases, which is called the black phosphorus and the blue phosphorus. Now, this is wonderful. Blue phosphorus is the phase which we are talking about, like buckled like this. And black phosphorus is like a stapler clip like infinite system. Now, this is a wonderful system for us. Hypothetical molecule, let us consider a phosphorine, two-dimensional phosphorus. All the 6-membered rings are planar. Now, it can undergo two types of distortion. One will take me to the buckled mode. The other one will take me to a stapler-like top. And let us see for our choice whether the theory of Jahn-Teller distortion explains both the phenomena to me well. So that is what we did, so you see. So what we did. So this is what I am taking. So you have this simple unit. One will give you a black phosphorus. The another will give you a blue phosphorus. And what we found out that the condition of pseudo Jahn-Teller distortion, the gaps are small and the vibronic coupling allows that. So we actually solved a 4x4 model here because there were 4 states which can interact with, and all of them satisfy the condition of pseudo Jahn-Teller distortion. Now, what are the other bigger consequences of this? The other bigger consequences of this, Prashantji is in the audience, is because something which has gained a lot of importance is what is called topological insulators. Now, you have a system like this, we know this, right? You have graphite or you have a graphene, and then when you make a one twist to it, you create what is called a topological shift. Now, because of topological shift, the valence band and the conduction band would get tripped over, and what we call as the band inversion. Now, band inversion occurs because of the change in the topology of the system. Now, since we have a system which is already topologically distorted, we thought maybe we can even have a little bit of topological insulator properties in these buckled-like systems. So this is what we tried to work out. For example, this is the distorted silicon germanium. Now the question is, why are we trying to work on silicon germanium, not only silicon? Because as we know, this topological phase will come when the spin orbit coupling is strong. So you want to go down the group to increase the coupling so that with a small distortion, you can get a topologically insulating phase. This is exactly what we found. And you see, this is the picture. So for example, when you have no strain, the valence band and the conduction bands are decoupled. Now, when you try to put a little strain, you make it more buckled. You see they are coming close, but still they have not tripped over. But now, when you have this spin orbit coupling between the two, you will see suddenly now the sigma bonds and the pi bonds have tripped over. Now, the valence bond, the top of the valence bond has properties of the pi orbitals, whereas the top of the conduction band has properties of the sigma bond. So, as a result, the change in the topology of the molecular structure also leads to what is called band inversion, which is a good test to show that you have a topological properties. Now, this of course we could also show it by various examples. See, when you have no spin orbit coupling, you see the states become semi-metallic. They are almost touching each other, but not tripping over. They will trip over when you have both distortion and spin orbit coupling. Oh, sorry. So this is the same thing which we found, and we have found this for a series of system for bismuth, arsenide, and so on. Now, see, this is just a toy model just to show you that this is, in fact, this is called the topological invariant. So, what you look at the change in the symmetry, and when we talk about the change in symmetry, we know that sigma has no parity, whereas a pi would have a parity. So, you just count the number of parities between the valence band and the conduction band, and if there is an odd parity, you will say that is a topological phase. Now, this is what we find. For example, here you see there is no topological phase. You see these are the pi electrons and the sigma electrons. Now, suddenly at when they make a topological insulator phase, the valence band and the conduction band get stripped over, and this is a consequence of again buckling, which is again a consequence of the eventually the consequence of the pseudo Jahn-Teller like distortion. Now, the remaining question here is, see, I have tried to tell you that there is a ground state and there is a low lying excited state which has the right symmetry to interact vibronically with the ground state. Now, the question is how many such excited states are there? Now, this is a question which is not known. For example, we don't know how much in the phase space or how much in the energy space I need to take into account to get the molecular distortion. Now, let us consider this case. Now, this is a case for silicene. Now, you see, if you have done a TD-DFT for this, which is the easiest thing to do, there are such 18 such states which are within 8 electron volts. Now, I don't want to solve an 18 by 18 pseudo Jahn-Teller distortion matrix. It is far difficult for me. I don't want to do it. So, can I do something which is more simpler? Can I fish out the more important orbitals which will tell me these are the states these are the minimum coupling you need to take into account to get the distortions right. Now, Weinhold has a nice model which he calls the natural bond orbital picture, which what you can do is you can selectively found out those orbitals and delete them. If deleting those interactions and reoptimizing the structure gives you the same distortions, you know those states are very important. So, this is a simple model which we did, and this is a model which we did, and we did work with these people. And so, the question is, so you see there are so many states which can in principle interact with the ground state. So, how do you find out which interactions are the more important interactions? In principle, each of them are symmetry allowed. So, what we did here is we selectively deleted those interactions and reoptimized the structure, and what we found that whenever we delete the sigma and pi star interactions, which Weinhold will call as NBO type interaction, natural bond interaction, donor to acceptor interactions. All of them are donor to acceptor interaction, but there are some of the very specific donor to acceptor interactions which which once you delete, when there are those no longer those second order interactions, the molecule flattens. So, we know that these interactions are the ones which are relevant, are the most important ones which are relevant. So, of course, this is what we did, and we found that this problem actually boils down to a sigma to pi star interaction. Now, we know from the day one that the reason why things buckle is because sigma and pi star separation, right? So, as a result, if sigma orbitals interact with the pi star orbitals in a donor acceptor sense, we know that the sigma pi mixing is these are the interactions which are responsible for the sigma pi mixing, and as a result, we know that these interactions are responsible primarily at an intuitive level for this kind of interactions. So, we could separate those interactions, and we could as a result reduce the phase space from a very large model to a small model. right? So I think this is the point I wanted to make here. So deletion of very specific hyperconjugative interaction. Now, see, the problem in computational chemistry is people, people very often explain the same thing using different ways of putting it. So what people in organic chemistry would call as hyperconjugation are the interactions which we call as donor acceptor interactions in our cases, right? So then if those specific hyperconjugative interactions are responsible for the molecular distortions, we call them as the predominant orbitals which are responsible for the pseudo Jahn-Teller distortion. The other important point which we have realized that, as you go down the group, for many of these late group elements, the structures are distorted. And I have a feeling that because of the pseudo Jahn-Teller like distortion, because the states are coming close, that probably provides an unification for the overall picture of the chemistry of oxides, sulfides, and other extended solids. So what we are now interested is whether we can have a vibronic effects, because these are very, very expensive things to calculate, whether we have very simple descriptors from machine learning models, whether, because we have a periodic table and we have a large body of oxides and sulfides. So can we have a machine learning approach to at least get an idea of vibronic coupling? And we know there is one thing is also very sure, that many of the late group elements are also superconducting. And at least from the BCS theory, we know that the vibronic coupling constant is proportional with the superconducting temperature. So these are some of the things which we are also looking at. We are also looking at the Moire patterns of the so-called van der Waals system. So you have two systems and you change them a small angle, say 1 degree or 2 degree, you have patterns. So whether the patterns are also dependent on the distortions here and the dynamical effects here. So these are some of the long-standing problems which we want to solve. And I thank you for your patience and look forward for your questions and suggestions. Thank you very much.
Thank you for a fantastic talk. Questions?
On the great work, I'm curious how you are removing the orbitals actually.
No, we are not removing the, see, this